Transformers are used exclusively for alternating current power transmissions and for various control and indication circuits. Knowledge of the basic theory of how these components operate is necessary to understand the role transformers play in today's nuclear facilities. These are the objectives for this course. A transformer is a device that transfers electrical energy from one circuit to another by electromagnetic induction. The energy is always transferred without a change in frequency, but usually with changes in voltage and current. Transformers are used in a variety of applications. The most important application of a transformer is for the raising or lowering of a source voltage to a desired level. A transformer can convert power at a given current and voltage to an equivalent power at some other current and voltage. Every transformer has a primary winding and one or more secondary windings. The primary winding receives electrical energy from an AC power source and induces electrical energy to the secondary winding. The energy appears as an electromotive force, or EMF, across the secondary winding, and if a load is connected to the secondary, the energy is transferred to the load. Transformers provide a means of transferring electrical energy from one circuit to another with no electrical connections between the circuits. A simple transformer consists of two windings located very close together. A winding consists of many turns of wire in the form of a coil, similar to an inductor. The primary and secondary windings are wound on opposite sides of the core and in the opposite direction. Therefore, the induced voltages are positive at the top of both windings during the half cycle of the input voltage. This relationship is also true if the primary and secondary are wound on the same leg of an iron core and wound in the same direction. The alternating current flowing through the primary winding causes an expanding and contracting magnetic field. The magnetic flux induces a voltage in the secondary windings. A voltage will also be induced into the primary windings, which opposes the voltage applied to the primary winding and is called counter-electromotive force. The primary field interacts with the secondary winding and induces an EMF across it. The ability to transfer energy to an electrically isolated circuit by means of electromagnetic induction is called mutual inductance. If the secondary windings of a transformer contain more turns of wire than the primary winding, more voltage will be induced into the secondary winding, and the transformer will act to increase the voltage. These types of transformers are known as step-up transformers. When voltage is increased, current is decreased. If the secondary windings of a transformer contain less turns of wire than the primary winding, less voltage will be induced into the secondary winding, and the transformer will decrease the voltage. These types of transformers are known as step-down transformers. When voltage is decreased, current is increased. Another function of transformers is to provide isolation capabilities. Recall from the discussion that there are no physical connections between the primary and secondary windings, only a magnetic connection. This feature ensures that the power source and the load are not electrically connected. Therefore, an electrical abnormality on one side of the transformer will not affect the equipment on the other side of the transformer. The typical transformer has two windings insulated electrically from each other. These windings are wound on a common magnetic core made of laminated sheet metal. The core provides a circuit of low reluctance or permeable path for the magnetic flux. The primary windings receive energy from the AC source. The secondary windings receive the energy by mutual inductance from the primary and delivers it to the load. The enclosure contains the transformer internals and cooling means. The two most common types of core assemblies are the core type, which is very commonly used in small transformers, and the shell type, which is more commonly used in larger transformers. This is an example of how transformers are used to distribute power from the generating station. From the generating station, a step-up transformer is used to boost the voltage and reduce amperage. This allows the electrical energy to be transmitted with less power and less heat developed over long runs of power lines. An area will have a substation step-down transformer where a sub-transmission customer, such as Aiken Co-op, will distribute the power to primary customers, such as hospitals, care facilities, or businesses where a loss of power would endanger life, and secondary customers, such as homes and businesses. Distribution transformers are generally used in electrical power distribution and transmission systems. This distribution class of transformer has the highest power or volt-ampere ratings and the highest continuous current rating. Normally, the power rating is determined by the cooling method and transformer uses. Some commonly used methods of cooling are by using oil, air, or some other heat-conducting material. There are two typical transformer ratings in most SRS facilities: 13.8 kilovolt to 480 volts AC, and 480 volts AC to 120 and 208 volts AC. These transformers are normally air-cooled.